17.5, Control of Muscle Contraction. Muscles are controlled as functional units called a motor unit. This is a single motor neuron and all of the individual muscle fibers that it stimulates. If an action potential is arriving on the motor neuron, it is going to stimulate all of these muscle fibers and they will contract simultaneously as a unit. We can have some motor units that are very, very small, maybe only 4 muscle fibers. So for example, the muscles that control very fine, discrete movements like the movement of the eye. These would be very discrete movements, very small motor units. In other cases, we can have up to 3,000 motor units. This would be the case if we need to produce lots of power. So for example, the motor units in the leg can be very, very large. Keep in mind they all have to contract simultaneously as a unit. So if we need a very fine, discrete movement, that's controlled by a small motor unit versus large motor units where we need to produce lots of power. An individual skeletal muscle can have many different motor units, and we don't have to stimulate all of the motor units within a muscle. And we can control how many of these are activated. This is a process which is called summation. If we need to produce just a little bit of power, we only stimulate a very few motor units. As we need to increase the amount of force, we can recruit additional motor units. So this will be a motor unit. We have the motor neuron, so it's axon, and then there are some branches of the axon. So in this case, there would be 3 muscle fibers that are controlled by this single motor neuron. The response of a motor unit to a single nerve impulse is called a twitch. And so we can graph this, and it would look like this. The force being generated is on the y-axis versus time on the x-axis. So beginning at time 0, we have the stimulus, and then there is a brief latent period where nothing appears to be happening. Actually, there is quite a lot that is occurring during this latent period. The action potential arrives at the neuromuscular junction. That has to spread to an action potential across the sarcolemma. That goes down the T-tubules. The T-tubules excite the sarcoplasmic reticulum, which releases calcium. Calcium diffuses through the cell, binds to the troponin, moves the tropomyosin, and then finally we get the myosin heads forming cross bridges. And whenever the myosin heads pivot, that contracts the sarcomere, and that contraction period then begins, and that is where we are generating force. And this all happens in a few milliseconds. Very quickly, that calcium is transported back into the sarcoplasmic reticulum, and so the binding sites on actin are once again covered by tropomyosin, and so there is nothing for the myosin to bind to, and we get the relaxation period, and the muscle is going to elongate. Can't do much work with the twitch. There's not a lot of force that is produced, and this happens very, very quickly. However, if we stimulate this muscle repeatedly, and so now there are multiple impulses arriving on that motor neuron, we can generate greater and greater force. So if you look at the diagram, the first little bump, that looks similar to the twitch that we've just seen. However, what if before that muscle can completely relax, another action potential arrives on that motor neuron? We're going to dump more calcium, and so we're going to repeat the contraction cycle. So as we stimulate a muscle with a greater frequency, we can stimulate it so quickly that the sarcomeres do not have time to relax. If we continue to increase, we get to something called fusion frequency, and so up at the top where the line flattens out, This represents stimulation at this fusion frequency. So action potentials are arriving very, very, very rapidly, and this muscle does not have the opportunity to relax. This is called a tetanus contraction. This is full contraction. This is maximal contraction and the maximum amount of force that can be generated by that motor unit. We can sustain that for a brief period of time, and then we will consume the ATP and also build up some lactic acid in that muscle, and we will begin to fatigue. And so the force generation will begin to decline. Energy for contraction does require ATP. We saw in the previous segment where the contraction cycle requires the energy from ATP to recock the myosin head. We can get ATP from a couple of different sources. There is a molecule called creatine phosphate. Creatine phosphate can transfer a phosphate group directly to ADP. And so whenever we are cycling between adenosine diphosphate, adenosine triphosphate, this creatine phosphate gives us a little shortcut. And so there is some creatine phosphate stored in skeletal muscle. Most of our ATP must come from glucose metabolism. So way back in lesson 7, I believe, we looked at aerobic respiration and how we can take fuel molecules such as glucose, break those down, and produce ATP. Again, this is kind of a little review of many of the things we've talked about earlier in the semester. We can have the anaerobic pathway, which is glycolysis. Glycolysis is very rapid, does not require oxygen. However, it is inefficient. We only net 2 ATPs per glucose. It is very rapid, however. Unfortunately, we begin to get some buildup of byproducts. If oxygen is not available, the pyruvate that results from glycolysis has to be converted into lactic acid. We can sustain very intense activity through these anaerobic pathways for about 30 or 40 seconds, and then muscle activity is going to drop off considerably. The aerobic pathway does require oxygen, and this is simply the cellular respiration that we looked at in lesson 7. So following glycolysis, that pyruvate is transported into the mitochondria as acetyl-CoA. The acetyl-CoA feeds into the citric acid cycle. Citric acid cycle feeds the electron transport chain, and we can make up to 36 molecules of ATP per molecule of glucose. So it is very, very efficient. It is slow, and it is limited by oxygen availability. So as we begin to work out and we increase the intensity of our workout, at some point we cannot continue through the anaerobic pathways, and we have to switch over to this aerobic mechanism. And then increased activity or sustained activity is limited by how much oxygen we can get to the mitochondria. Oxygen, remember, is necessary in that final step to make ATP. So the purpose of aerobic training, and this is nice, this ties together so many things that we've discussed throughout the semester. Think about respiratory system and the cardiovascular system. Those work hand in hand to deliver oxygen to the mitochondria. And so as we work out, we are increasing the efficiency of the respiratory system. We are increasing the efficiency of the cardiovascular system, so we can in fact deliver oxygen more efficiently to the muscles, and we can sustain vigorous activity for longer periods of time.